Swayam Prabha. Digital India. Educated India.
So, welcome back. As we have discussed many points in the previous lectures about the drainage, or we can say this channel shape, or the peak discharge and all that in different areas, the river basin. Let us see how these parameters are important in understanding the overall flooding events. So, mainly this is what we do in free well geomorphology, is that we try to look at the linear aspect of the channel system, aerial aspect of the drainage basin, channel geometry and process domain, integrating hydrology and geology. Few things we will discuss in this lectures. So, coming to the linear aspect of the channel, what we see mainly is try to understand that what is the surface area, that is the basin area, what is the drainage pattern, stream order, where we can do the quantification of the stream network, bifurcation ratio, drainage density. So, this all parameters are going to help us in understanding that what will be the flooding conditions in the drainage basin. So, usually what we do is that if you have the major trunk stream, then the area which is like flowing, last time I was showing you that you have like two sloping surfaces here. So, streams which are flowing here like this, and then you have the main trunk stream, and the streams are getting into this here, and then few streams are flowing, and maybe I can draw it little better. So, suppose one trunk stream is like that, and then you have the streams or the tributaries which are joining here. Another trunk stream is like that, and then you have the streams which are joining. So, this will have what we will put as, and this is one basin area, and this is another basin area. So, this is what is exactly has been shown here. So, you have the main trunk stream, and then you have the tributaries which are joining the main trunk stream. So, ordering of the stream will also be important, because the ordering will help us in getting the bifurcation ratio of any particular basin. So, we have one is the main basin of the major channel, that is in fourth order. How we order this, I will explain. And then we are having the sub basins. These are all smaller basins which are feeding the main trunk stream. So, what has been done is that the boundary here, we have two smaller streams, or the or first order, with if they joins here, then this becomes the second order, and two second order streams when joins become the downstream stream will be considered as third order, and when two third order stream meets, then it becomes the higher order. So, this is what we usually do. So, and then coming to the drainage pattern, which is again an important part, because this will help us in identifying the subsurface geology. So, for example, if you are having the dendritic patterns, we will come to that how it looks like. Okay, then what straight away we can identify that it shows homogeneous geology, horizontal or gently dipping stratas. In such regions, usually we will be able to find the dendritic pattern. So, what we were discussing earlier was straight channel, meandering channel, and the braided channel here. But here what we are looking at is the drainage pattern. So, you need to be careful in distinguishing or putting the terminologies. So, trellis pattern develops over tilted or folded strata. Radial patterns develops over domes and volcanoes. So, along with the geology, one can also identify the landforms on which the drainage or the drainages are developed. So, drainage pattern dendritic mainly is a typical irregular branching pattern, and it looks like a tree. So, you have a tree pattern and the streams are flowing in many directions. It is common in massive rocks and flat lying strata or slightly inclined strata, and due to the it is developed due to the strong resistance of the rock, headward development of the valley is negligible. So, in some cases you will find that. Okay. Then parallel streams or subparallel streams are commonly seen over a sloping surface. So, you can also judge based on such pattern that in which direction the slope is. Common in terrain with homogeneous rocks, development of parallel rills or gullies or narrow channels are commonly seen on gentling sloping surfaces. Then coming to the radial, as I told that it will also help us in identifying the landform, either it is a dome or it is so this portion is the central portion is elevated, so higher, and this one will be sloping in this direction, so away from the center, and that will give you a typical radial pattern. Then we have rectangular channels, which are mostly seen where you have the jointed and fractured terrain, and it will typically show that they intersect or bends at the right angle. So, in most of the massive rocks or fractured rocks or foliated metamorphic rocks, you will be able to see a typical rectangular pattern, drainage pattern. Trellised, so you have again rectangular channel arrangements where the main stream are parallel and very long. So, main stream will be parallel and very long, and this pattern is commonly in the area where you are having the folded terrains or you are having an alternate of weak and resistive rocks. So, you will be able to see in folded sedimentary rocky terrain where you have the weak and resistive rock forms long parallel belts. So, which has been seen here. Annular stream follow almost circular or concentric path along the belt of weak rocks in an area which are marked by domes and basins. So, these are typical of different type of drainages, and these are the most common one. So, you have dendritic drainage, typical tree shape, and then you have radial. So, either you have an elevated portion or the domal areas, or you are having the volcanic cones, then you will see a radial pattern. In the area where you are having well developed fractures and joints, then you have rectangular pattern, and trellised mostly in the areas where you are having folded sedimentary rock succession and with softer and or weaker and resistive rocks, alternative succession of that if you have. So, then you will see a trellis pattern there. Quantifying stream network, stream in a basin can be ranked using one or several schemes. So, we are talking about the flood intensity. So, the flood intensity is considered to be a discharge along channel over time, and this will be influenced one by the runoff, the channel pattern and shape, and the number of tributaries, and the distance downstream at a point of interest. So, the stream order, usually what we do is, I was explaining in the previous slide, that the smallest tributaries are designated as first order, and then further if two first order joins, then you have second order. So, for example, at the time of the origin or the upland areas, so this will be the first order stream, and then if you are having the other one joining here, then this will become second order, this will be first order, this will be first order first, and this will be second, and 2 second order will become third order, and similarly if you are having the second order stream, 2 second order two third order joining the main stream, then that will become the fourth order stream, and so on. So this will play an important role when we are talking about the bifurcation ratios and the drainage density and all that. So drainage density mainly we will see consider the overall area of the basin and the length of the streams, all streams. So low order streams have shorter lag. This is important for us. So if you are having more number of lower order streams, then you will be able to see that the peak discharge or the hydrograph will be very sharp, or it will be the flooding conditions will be very quick between the rainfall and the flood events. So lower order streams have shorter lag times between rainfall and flood and are more prone to flooding. Higher order streams with many tributaries are less prone to. So this you please remember, that is the lower order stream, short lag and prone to flooding. Higher order with many tributaries, less prone to flooding. So the quantifying stream network, stream order, what we take is streams in the basin can be ranked using one of the several methods. So this what we have already discussed, so I'll move ahead. So if you are having the streams or the drainage which has been shown here, so you have two smaller streams joining, making it second order, 2 second order, making it third order. So what you can do is you can easily calculate the bifurcation ratio which has been given as Nu by Nu plus 1. So higher order stream, the next higher order stream. So where Nu is the number of segments of a given order, and then Nu plus 1 is your number of segments of the next higher order. So for example, if you are having Nu is 10 here, that is this one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the next higher order is only 3, that is 2, then you will have the bifurcation ratio 3.33. So usually what has been we understand is if you are having high bifurcation ratio, then you will have high discharge, and if you are having low bifurcation ratio, then you will have low discharge. But again, it will depend on the shape of the basin. So this is just the correlation given between the first, that is the lower order, and the ratio between the next higher order. So what we see over here. So drainage morphometry and its influence on discharge. So it is extremely important for us to understand the peak discharge of any particular drainage basin or the stream, because it is considerably important, for example, in deciding upon the size of the culverts, bridges or causeways during highway construction. And so this part plays a very important role when we are talking about the flooding conditions. So drainage network of river basin, shape and channel pattern are most vital morphometrical factors that play significant role in increasing rate of flow through the drainage system. Even with higher RB values in an elongated basin, that what I was talking about, that even though we consider that a high bifurcation ratio will show us that there will be a high discharge, and low bifurcation ratio, low discharge, but eventually it will depend upon the shape of the basin. So in the basin where the higher bifurcation value in the elongated basin, the hydrograph is very smooth. whereas what we should have expected is that because it is having higher bifurcation ratio, the hydrograph would have been slightly peaked up or maybe a sharper one, but it is quite smooth as compared to the rounded basin. So if you take an example here, so one is we are having the elongated basin where the bifurcation ratio is higher. So in this case we should have expected that there will be high discharge. And then another one with a similar area, this is just the sketch to explain you. So what we see here is that rounded basin, the next one here, with the same basin area having low RB value bifurcation ratio shows high discharge, which is completely opposite what we learn. Okay. So you have the hydrograph, that is the discharge versus time. So in terms of the elongated basin, even though it is having higher bifurcation ratio, the hydrograph is quite smooth, whereas in this case the hydrograph is different, and very quickly the basin enters into the stream enters into the flooding state. So the reason here is that the smoother curve of the narrow shaped, that is this one elongated basin with high bifurcation ratio, can be explained by greater lag time. So the lag time, that is the time to reach this point, the water to reach this point through the streams it takes more time for the water to reach the outlet. This is an outlet here, the major trunk stream, whereas the time taken from the upper, middle and lower reaches in the rounded basin is less, causing higher discharge. So along with the bifurcation ratio, one has to take into consideration the shape of the basin. Then we have another important parameter, that is your drainage density, and the drainage density is basically given as a ratio between the total length of streams in the basin and the drainage basin area. So D is the length of the channel per unit area, that is in kilometer per kilometer square. So it has been given as D is equal to sum of the length of all the channels within the basin upon the length of the channel per unit area. Now this plays an important role because the measurement of drainage density provides any hydrologist or geomorphologist a very useful numerical measure of the landscape dissection and runoff potential. So in flood this also plays an important role, but this will be governed by the geology or the lithology of the area. So on highly permeable landscape with small potential, the potential will be very less of runoff because it is permeable, so the percolation will be very fast. The drainage densities are sometimes less than 1 kilometer by 1 kilometer square. On highly dissected surfaces, drainage densities of over 500 kilometers per kilometer squares are often reported. So you will have higher values there. So closer investigations of the processes responsible for the drainage density variations have discovered that number of factors collective influences the drainage density. So one is, those factors are climate, topography, soil infiltration capacity, vegetation and geology. Some factors we also discussed in the landslide, whereas here also, because they are all related to the topography and the precipitation, the similar factors are responsible for putting the channel in flooding state. So if the infiltration dominates over runoff, tends to have lower drainage density. So if you look at the drainage texture, considering the different type of rocks, either this is basically the the igneous rocks, gabbro, granite, sandstone, sedimentary rock and shale. So the drainage texture varies from coarse to fine. So the drainage texture is defined as relative spacing of the drainage lines, that is the small tributaries or the main one, commonly termed as coarser if you have low drainage density which develops on hard resistive rocks or over highly permeable material. So you will have very few drainages which are available, so we term this as an coarse drainage. If you have medium and moderate density, it develops on hard rocks with moderate permeability, fine grain, closely spaced. We are having develops over on loose or poorly cemented rocks, example clay, silts, or you are having low permeability in it. So different type of rocks and related drainage textures are being shown here. So we are having coarser, and then we are getting into the finer texture. So this can also help in understanding the discharge also. So for example, if you take this basin which has been shown here, so this portion is mostly sandy area. So sand is more porous, so the area doesn't allow much of the runoff because it is percolated down, and you have the less amount of water which has been seen in the channel, whereas in this region which is different within less porosity will have more drainage drainage density. So sand promotes infiltration, eventually result into the low drainage density. Basin shape, as we were talking about, the can also be connected with this one, that where exactly you are located. Either you are located in the upstream area, or you are located in the middle part of the basin, or in the downstream area. Accordingly, the hydrograph will change, that is the time lag between the rain and the flood. So if you have different basin shape, you may expect a different peaks or the hydrographs with respect to the time and the discharge. So as I told that peak discharge of any channel is important. So this is the basically very simple exercise, one can do it to identify the cross sectional area. So if you are having the channel cross section is around 25 square meter, and then stream velocity is 5 meter per second, then you can have the discharge at that particular given point around 125 cubic meter per second. So if the cross section area varies, then you will have, and if you keep the velocity as same, then you may have the flooding conditions in the nearby areas. Stream order is important, as I was discussing, that lower order stream tends to respond rapidly to the heavy rainfall or storm with steep hydrograph, because water has to travel only a very short distance. So the smaller streams, more number of smaller streams will result into very quick flooding state to the main stream. Hence, such streams provide less time for flood warnings for the downstream residents, because they have smaller drainage basin and it carries coarser and larger sediments from a given area, whereas higher order streams with numerous tributaries have longer lag times between the storm, that is rainfall, and you are having downstream flooding. Their hydrographs are less peaked and cover longer time lag, there is a time period, and it remains for a longer period. So flood warning can be issued in such situations, because you will have the longer time gap between the rainfall and the flood. Now, there are ways to understand and identify that the recurrence time or the recurrence interval of the flood events, if you are having good record of that particular region. What has been shown here, this is from Colorado and from the Big Thompson River. The data is almost from 1951 to 1975, and here it gives the peak or maximum mean discharge in one day, and accordingly this has been ranked. Okay. So ranking has been done, like first the maximum discharge in the record, then second. So this ordering has been done based on the maximum discharge. So how to calculate this recurrence, we will see in the next slide. Okay. So for example, 10 such cases have been ranked, okay, from 1 to 10. So how to calculate is not very difficult. Suppose the record of maximum mean discharge by a particular stream each year have been kept for n years. Each of this yearly maximum discharge can be given a rank, which we were showing, rank 1, which stands for the maximum discharge in this years, and the recurrence interval as R equal to n plus 1 by m. So where n is the number of years of records, like say 25 years record is there with us. So in 25 years the maximum discharge was recorded during 1956. You take the previous example, and the discharge was 1520 cubic feet per second, which ranks first. So in this case, the similar type of flood can be expected. If we would like to know the probability, then it will be 25 plus 1 by 1. That means every 26 years you will have the similar flooding event. Okay. Or if you want to find out the recurrence interval similar flood that occur during 1971, then we can have, because it was been ranked 7th and the peak or the maximum discharge was 1030, and then we can have the recurrence interval be around 3.7 years or around 4 years. But most important part here is that whether the conditions remain same or there was an alteration or some changes were been made in the drainage basin by humans. So that may have the different scenario what we see here could be affected. So thank you so much. We will continue in the next lecture talking more on the recurrence, as well as few points we will discuss, that how the urbanization and if you are is getting affected without, when we do not consider the landforms and do not having the understanding of the peak flood discharge or the maximum discharge of that particular channel. Thank you so much.